welcome to the session about the Opti pager. There has been some double booking, so if you're for another session, it has been relocated to Tokyo.
I think it was about introducing Asper. That session has been moved to Tokyo. So that it was first listening to them she's talking about.
Yes, so let's okay. Wait. Yes, welcome to this session on the Opti pager. It's a recent feature we have added to Opti. It enables Opti to run on systems where you don't have enough secure memory to load the entire Opti binary into memory. This could be on systems where trust-protected DRAM isn't considered secure enough, so you need to run on system RAM, and system RAM is usually, you don't have that much available. So what we do is that we have a virtual memory space, which all of it isn't mapped at the same time, and we use DDR as backing store. You could compare it with swapping that we do in normal world in Linux, for instance. So we have partitioned the memory space we use in Opti into several areas. We have unpaged code and data, which is basically the stuff that is needed by the pager to operate. And then we have some initialization code, which is used during boot, but also during runtime when you turn off and on cores. And we have one section which is page code and read-only data. This is the section that is served by the pager. So this is where the pager is active. Then we have one area for unpaged memory, heap, exception stacks, and translation tables. By the way, if you have any questions, feel free to just interrupt. So, what happens during a page fault? First is to validate the address to see that it's within an area that we can serve, because if it isn't, then it's an error in the code, and we activate some abort handling instead. Once the address is verified okay, we try to locate a free page and map it at the required address to be able to populate it with the new content from backing store. After that, we can validate the content with a pre-computed hash, which is stored in secure RAM, and resume execution. I will go into the details in the following slides. So we have a list of address ranges which are valid, or which we handle. It is code and data, of course, but we also have paging of the stacks, or it's not actual paging, it's demand allocation of memory for the stacks. But we share physical pages with the pager. I will look into that a bit later also. Each address range has a flags field which describes its usage, if it's read-only, read-write, which is stacks then, or executable. To find a suitable page to use as a free page, we use an approximation of the least recently used algorithm in order to find the oldest page. Since we only page read-only pages, we don't have to write out dirty pages or anything like that, because all pages are clean and we have the same representation in the backing store. When we populate the page, we copy data from backing store, DDR, and verify the content against the pre-computed hash, which we store in secure RAM. An interesting something to keep in mind when you do this hash verification is if you use dedicated hardware for hash verification, you need to be able to handle the case where you already have an ongoing hash operation, since that could very well be the case if you're running hash operations when an abort occurs. The page replacement algorithms. We have all the pages in a queue, ordered from the oldest to the youngest, where when we need a free page, we take the one that is at the beginning of the queue, because that is what we consider the oldest. And we remap the page to the new address and populate it, etc. And put it at the end of the queue as the youngest page. 1/3 of the pages in the beginning of the queue, which are the one that are the oldest pages, we map them as no access to be able to trap accesses to these pages in order to see if they are used or not. If they aren't used, they will remain old and be reclaimed at some point. But if it happens that we get an abort because someone is accessing this page, it is obviously used, and we will put it, remap it with the original permissions and mark it as the youngest page again by putting it at the beginning of the queue, or end of the queue. We have several stacks in the opt. We have exception stacks, and we have thread stacks. We have some temporary stacks when entering and exiting opt also. But the thread stacks are the ones that are large. They can be 4, 8Ks large, depending on the use case. And we have currently support for up to 3 threads that can run, not in parallel, but they can be at least allocated. And that's quite a lot of memory that is needed if all those stacks should be allocated at the same time. But if we instead allocate each page of the stack when it's needed and remove it, the physical page from the list of pages that the pager can use, that means that we get a bit more efficient pager, since it has more pages to work with at the same time. We have enough pages for stacks, even if we have to run with degraded performance. once a stack isn't in active use, for instance, if the thread is suspended or terminated, we can return the pages that we don't need for the moment in the stack, or the complete stack where when the thread is terminated. This technique can also be used for other allocations. It doesn't have to be stacks, it could be other data where we allocate complete pages at a time. Not very suitable for the heap though, since the heap uses smaller chunks and it's likely to get fragmented and wouldn't return pages again. So we have some limitations on what we can do with the pager. We can only page read-only data, since it would be quite expensive to do encryption and all that would be needed when we do a page out, and also it would be a bit more complex. So at least as a first step, encryption is it's not there. And also if we were to have a page, for instance a heap, it would probably not help very much, since a heap consists of a large linked list in some way or the other, and we will probably touch most of the pages while doing free and allocate. Some of the initialization code and exception code can't be paged. Obviously not the pager itself, since it would be a deadlock. But also when a CPU is turned on, let's say that the system has booted and all the CPUs are up and running, and then you start to turn off, and when you turn them on again, you still have to do some kind of initialization of the CPUs, while the pager isn't, you haven't configured MMU, etc., so you can't really page. And then we don't have support to page trusted applications either. That's something for the future. So when we boot, we only have to put part of the Opti binary into secure RAM. We need to have the code that is needed to initialize Opti, and we have to have enough memory for translation tables and all that. But the page part of Opti doesn't have to fit. That's the idea. So we have a header of the binary that is used by the loader to understand which parts should go into secure memory and which should go into the DDR. And then when Opti is booted, the address of the page part in DDR is supplied in one register. And in this initialization section, we also have all the hashes of the pages that we have in DDR, since we have to be able to verify them before we can use them. And all these hashes are pre-computed when creating the binary. Do we have any questions? Booting.
So doing the loading to DDR, do you need to do some kind of relocation, or the code is just position independent?
It's linked at the fixed address. so we have to load it at the correct address.
So it means you can actually use SLOT on different platforms.
So is there any limitation for the page size or number of pages?
Well, the page size is more or less fixed because of the platform, and we use 4K pages. Since we have so little memory, we probably want to use the smallest possible page size all the time to have as many pages as possible. We don't really have a limit on how many pages. Currently, we only support using one descriptor table, but that's 1 megabyte on B7 with small pages, and it's 2 megabytes on AH 64 with long descriptor format.
You said in the limitations that the secure apps can't be paged. Is that something that's addressable, or is it intrinsic to the problem that you can't do it? Because presumably you have to mark things like secrets in the secure app if you're going to do that.
No, it's just that we haven't done it yet, and also it will require even more memory. So the choice we have made is that the opt itself that runs in kernel mode, that is the most sensitive part. We can hide secrets there and all that things, and that has to be as secure as possible. And even if the purpose of the OS is to run applications, the applications are less prioritized in that way, since the secrets doesn't have to leak out into the applications all the time. But given that you have maybe a bit more system RAM, it's probably interesting to be able to run at least some trusted applications in system RAM, and then we would use paging technique, I guess.
Why we should do the first we set the page attribute as no access, and then we need to do the checksum verification and reset the page attribute to accessible.
Sorry, could you repeat?
Just in the page you said the page you map to the low access
Yes.
attribute. So why we need to do that step? Because if the page have no data, so you have to do the verification.
Here when we are when the page is getting old and we mark it with the no access, the content of the page is still okay and up to date. So it's just a way of knowing whether someone is using the page or not, because if someone is using the page, we are bound to get an abort quite soon, and then we can make it young again. This algorithm works better the more pages you have, because then they have a longer time in this gray zone where they have mapped as no access.
What's the third? A guesstimate or a benchmarked number?
Sorry?
You said a third of the pages are no access.
Yeah, it's...
Was that a guesstimate, a paper, or just
it's a guesstimate. Yeah, we have used it for some time, and it seems like it's a good choice. You shouldn't have too many, because then you get many faults, even if they are very cheap, these faults, since you don't do very much. On the other hand, if you have too few, you risk having to page in a page that you just dropped, and that's a bit more expensive since you need to do a hash verification of 4K. Currently I've been able to run Opti with 200Ks of physical memory. We are trying to push that limit, but yeah, it's a lot of work to optimize all the different parts to minimize memory and also use memory in a more efficient way. For instance, with this technique we are using for the pages, for the stacks.
I think we reduced memory usage to the half since last connect.
Yes, even more than that,
Yeah.
I think.
So it's going in the right direction at least.
Absolutely.
So I guess you're speaking about the 32-bit of T. You expect more memory in 64-bit or?
I don't know really what could be expected. It seems
Use a page table.
I mean, for AH64, we will probably need more memory because even if some of the memory can be mapped quite efficiently with the large descriptor format, we have some parts of the memory where we can't do it so efficiently, especially the trusted applications, because there we will use at least 8K translation tables.
So the pages that are in system RAM, they are not readable by OS or something, right?
Exactly, they are trust zone protected. The pages that we have in DDR doesn't have to be trust zone protected since we have a hash that we verify, but it can be a good idea to try to have them trust zone protected anyway in order to make it harder for normal world to accidentally overwrite the memory. Since an invalid page would result in
Yes.
error handling. Yeah, it would be a bad hash and we would have to just abort.
Jens, when you're copying the pages into the SRAM, before verifying them, are you mapping them as executable already? Or are you
For the moment we are actually, but on the other hand it's completely single threaded right now, so
right, so the other cores can't be executing.
yeah. For multi-threading then it will be interesting. We will need to map at a different address then, I guess.
Well, you could also map it as, you have to map it as read-write.
Yes, read-write, but
Then you
also
might
at a
get no
different
extra.
address, since it could be, it doesn't have to be a prefetch abort, it could be data abort also.
Yeah, so you want to avoid having the other cores that think they could read something that you haven't verified.
Exactly.
So in terms of performance, is DRAM is faster than secure RAM or slower?
Secure system RAM is usually a bit faster, I think. So the use case in normal world is to use them for some performance stuff. So that's kind of a struggle between security and performance of other use cases.
So in this case, it would be faster just to load from your non-volatile storage to DDR, and after to copy some permanent memory into a secure RAM, just to erase all your DDR. All the
I don't follow.
So I guess in the current case, you are loading from your non-volatile
No, we're loading. When Opt is loaded at boot, the init part is loaded into system RAM, and the page part is loaded into DDR. And then when we need the data, we copy it in from DDR into system RAM on demand. Yeah. And it would have been a lot faster to run just in DDR without all this paging, of course, but
Security.
yeah, security. But the penalty isn't that large actually. I've been doing some experiments, and you don't really, in most use cases, you don't notice the difference. It's if you happen to be in some code path that uses many pages, then you will notice. But if you have good locality, then it's no problem.
Where do you store you expected hash value?
We store them in system RAM, in secure system RAM. So it's close to the code that is used by the pager itself. So it's in secure memory.
So after you update the data in the RAM, and before you write back to DDR, you need to update the hash value.
No. The thing is that we only page read-only pages. So we don't need to page out. Because if we were to page out, we would probably need to encrypt it also, since it would contain something secret.
So all hashes are pre-calculated during build time and put into a special section.
Yes.
When we found the hash value isn't correct during the paging, and the OPT just crashed.
Yeah, it will be kind of a controlled crash because, yeah.
Okay, for device which is running OPT, then the device will have to be rebooted.
Yes. We could perhaps improve default handling a bit to maybe release the core out in normal world again and just refuse entering secure world or something, just to be as friendly as possible to normal world. But yeah, that's a future feature. So, no more questions. Then I think we can close this session. Thank you for your time.